Hi, I'm Arun, and in this video, I'll be discussing our recent results on privately answering counting queries via generalized Gaussian mechanisms, and this talk is based on joint work with Jiazheng Zhao. So to give a brief overview of the talk, I'll start by introducing the counting queries problem, as well as generalized Gaussians and the motivations behind them. And then we'll move on and analyze the generalized Gaussian mechanism, both its privacy and its error guarantees. And then we'll conclude by discussing some interesting future directions in this line of work. So in the counting queries problem, we're given a vector D, which represents some statistics about a database containing users' private data. And our goal is to find a mechanism M that outputs a noisy copy of the vector D. We'll denote the distribution of noisy vectors output by the mechanism by MD. And our goal is for this noisy distribution to balance the goals of privacy and utility. So for this talk, by privacy, we'll mean epsilon delta differential privacy. And I see most of the audience is familiar with what that means, or at least slightly familiar. But in case anyone isn't familiar, basically it means that for two databases that differ by at most one individual, the distribution output by the mechanism is not too different. And we'll go into some sufficient conditions for this later in the talk. So in the setting of counting queries for two adjacent databases, their corresponding vectors, we have the guarantee that the L infinity norm of their difference is at most one. So the idea is these vectors, the statistics they're tracking, are counts of the users in the database that satisfy some property. And so adding or removing a single user can only affect these counts by at most one. That is to say, it can only affect the coordinates by at most one. Okay, so again, just to recap, by epsilon delta differential privacy, we mean that if the mechanism takes in two vectors d, d prime that satisfy this adjacency condition, then the resulting distributions have to satisfy some sort of statistical closeness. Okay, so this is our privacy goal. So then what should our utility goal be? So we're going to say that we want the mechanism to have low error, and there's multiple different types of errors we could consider here. So one type of error that's well understood is the L1 error. So the L1 error is if I look at the expectation over the noisy vector d tilde, and I look at the L1 norm of d tilde minus d divided by k. So effectively, this is just saying what's the expected amount of noise I add to each coordinate of d. And this is well understood because the Gaussian mechanism, which takes d and then samples x from a multivariate Gaussian, and then outputs d plus x. If you set the covariant, or if you set the variance of the Gaussian appropriately, then you get epsilon delta differential privacy, and you also get that this mechanism's L1 error is what we'll denote by opt, which is on the order of root k log 1 over delta. And this is the best possible L1 error you can achieve for the problem. So one type of error that until recently was less well understood is the L infinity error. And the L infinity error is just the expectation of the L infinity norm of d tilde d minus d. So put another way, it's the expectation of the maximum amount of noise added to any coordinates. And here the Gaussian mechanism gets error opt times root log k. And this is because for a k-dimensional multivariate Gaussian, we expect that its largest coordinate is root log k times larger than its average coordinates by union bound. So a question that has been studied in the past few years and we've recently resolved as a community is whether it's possible to avoid this root log k factor for L infinity error in the counting queries problem. So in this talk, we're going to consider using a generalized Gaussian mechanism instead of a Gaussian mechanism for the counting queries problem. So why does a generalized Gaussian mechanism make sense? Well, let's first talk about what generalized Gaussian actually is. So recall that a Gaussian mechanism adds noise drawn from a Gaussian, and a Gaussian has PDF proportional to exponential in the negative L infinity or L2 norm squared divided by some scaling parameter sigma. So all a generalized Gaussian is we'll say the generalized Gaussian with shape parameter p. It just has PDF that's exact same as the Gaussian, except we replace the L2 norm and the squaring by the LP norm and raising to the pth power. Okay, so why is this a hopeful candidate for the counting queries problem? So if we look at this graph of the Gaussian in blue and the generalized Gaussian with shape parameter 8 in purple, and both of these are plotted with sigma equals 1, then what we'll see is that the generalized Gaussian's tail falls off much faster. So we expect that for a multivariate generalized Gaussian, its largest coordinates are not going to be too much larger than its average coordinates. However, we can also see that the generalized Gaussian takes a while to start falling off compared to the Gaussian. So around 1.0 is only on this graph is where the generalized Gaussian starts falling off, whereas the Gaussian, it starts falling off much earlier. So this sort of tells us that while the generalized Gaussian gives us better tail bounds on each of its coordinates, or a better ratio of the largest average coordinate, its average coordinates are probably going to end up being larger than the Gaussian mechanisms. Okay, so what we're going to consider in this talk is what guarantees do we get if we use a generalized Gaussian mechanism? That is, we add noise from a generalized Gaussian instead of a Gaussian. Okay, so the results we get in this talk. So to contextualize these results, the term opt we defined earlier as the optimal error in the L1 error setting is also actually the optimal error in the L infinity setting. That's a result of Stanke and Ullman and some recent work. So our main result for this talk is that the generalized Gaussian mechanism with shape parameter p achieves error that's worse than optimal by root p times log to the 1 over pk, assuming p is not too large and delta is not too small. In addition, we can compose the generalized Gaussian mechanism with the sparse vector mechanism to improve the log to the 1 over pk to a log k to the 1 over p dependence. This result is more technical, builds on some previous results rather than using new ideas. So I'm going to be mostly focusing on the first result, or what I've denoted the main result here in this talk. And besides these quantitative bounds, I think what is qualitatively nice or interesting about this paper is that it gives the first closed form analysis of the generalized Gaussian or generalized Gaussian mechanisms in the DP literature. So before there were some papers which considered using generalized Gaussian mechanisms, but they only gave non-closed form bounds, which aren't necessarily useful in theory or practice. So here we give actual closed form bounds, and this will hopefully bring the benefits of using generalized Gaussians closer to fruition. Okay, and just to contextualize how good our upper bounds are compared to previous and future results or following results. So again, recall that the Gaussian mechanism is well known to achieve the optimal error times root log k. And what Stanke and Ullman showed, the first result to beat the Gaussian in the L infinity error was that if you compose the Gaussian with a sparse vector mechanism, then you can improve the log k to root log k. So if you optimize for the choice of p, then our first result shows that the generalized Gaussian can also achieve opt times root log k. But there are some nice qualitative differences between our results. So namely, because we avoid using the sparse vector mechanism in this result, we maintain that the distribution is closed form and also marginally independent on each coordinate. Okay, if we are willing to use the sparse vector mechanism, then our second result lets us, for the right choice of p, achieve L infinity error oft times root log k. And then in some follow-up works by two different groups, they showed that actually two fairly different mechanisms, both of which I think are very interesting and insightful, can achieve the optimal error up to constants. That being said, I think there are, again, some qualitative reasons to prefer using a generalized Gaussian over these following results, but that also goes both ways. I think there are some qualitative reasons why the following results are maybe nicer or cleaner than our results. And I would encourage you to read our paper or the other papers for a discussion of these ideas. Okay, so now that we've talked a bit about the problem and what's known, let's go ahead and move into the analysis of the generalized Gaussian mechanism for this problem. Okay, so we'll start with the privacy analysis. So again, recall that the mechanism of interest adds noise x to d with probability proportional to exponential and the negative LP norm of x, rescaled by sigma all to the p. So the sufficient condition we'll use for epsilon delta differential privacy is that if we sample a random noisy vector tilde d from MD, and then we look at the log likelihood ratio of MD and MD prime at this vector, then the log likelihood ratio shouldn't exceed epsilon with probability more than delta. Okay, and this is nice to work with because if we just plug in the generalized Gaussian mechanism, so I guess first I should say we can assume without loss of generality that the two vectors d and d prime differ by the all ones vector. This is because the noise distribution we're using is symmetric, so it doesn't really matter what the signs of the difference d minus d prime are. So we can assume the signs of all the coordinates are positive. And then we might as well make the coordinates as large as possible to sort of maximize the privacy loss, quote unquote, of using the mechanism. Okay, so without loss of generality, d minus d prime is the all ones vector. So with this assumption, we can just actually evaluate what the log likelihood ratio is. And we get that the log likelihood ratio is going to be x plus the all ones vector, the LP norm of this to the p, minus the LP norm of x to the p, all over sigma to the p. Okay, so sorry, I should say, it suffices then to basically tail bound the numerator, which is the difference between these LP to the P norms. Because if we can get a tail bound on the numerator, then we can just solve for the value of sigma that sort of rescales this tail bound to get to become the sufficient condition for privacy. Okay, so to tail bound the numerator, so without loss of generality, we'll assume P is even. This is just to avoid a bunch of absolute value signs flying around in the analysis that can be kind of messy to work with. Okay, so since we're looking at the difference between two LP norms to the P, we can decompose each LP to the P norm as the sum of the powers of the coordinates. So we get that the difference between these LP to the P norms is sum over j of xj plus 1 to the P minus xj to the P. And then we can just use calculus to rewrite each of these differences, or to bound each of these differences by P times xj plus 1 to the P minus 1. Okay, so now we want to tail bound this quantity P times sum of xj plus 1 to the P minus 1. The problem is that xj plus 1 to the P minus 1 is somewhat hard to work with, because if we basically expand out this expression, we're going to have the sum of a bunch of different powers of xj. So it'd be easier if we just had one power of xj to work with. So the way that we'll get around this issue is we'll observe that when the absolute value of any xj is small, in particular because we had an upper bound on P in our result, we can settle for when xj is at most root k. Then it'll turn out that for the eventual choice of sigma we use, when the absolute value of xj is small, then xj plus 1 to the P minus 1 is basically a lower order term and we can ignore it. So we don't have to worry about those. And then when xj is large, xj and xj plus 1, even when we raise them to the P minus 1 power, they differ by basically like 1 plus little o of 1 factors. So we can basically treat xj plus 1 to the P minus 1 as being roughly equal to xj to the P minus 1. There's some technical details I'm skipping over here, but for purposes of understanding, this is really all you need to know, is that basically just using this case analysis, we can treat xj plus 1 to the P minus 1 as being xj plus to the P minus 1. Okay, so again, just putting it all together, we get that we can approximate this harder variable to work with just sum over xj to the P minus 1. So how are we going to analyze this sum? So our observation is just basically by using a change of variable formula. You can see that when xj is sampled from the generalized Gaussian, then the absolute value of xj to the P minus 1 is a generalized gamma random variable. And then there's a technical lemma in our paper where we show that the generalized gammas with the parameters that arise from the setting are sub gamma. And this is mostly technical. There's not really too much interesting going on in that part of the paper, besides just working through some math. Okay. So now we can just use sub gamma tail bounds to show that this sum is at most root kp log 1 over delta times sigma to the P minus 1 with probability 1 minus delta. Okay. So again, recall that we want that the privacy loss is at most epsilon with probability 1 minus delta. So if we plug in this upper bound on the numerator of the privacy loss, then we solve for sigma. We see that we want to set sigma to be root kp log 1 over delta all over epsilon, which is equal to the optimal error times order root p. And then this will give us epsilon delta difference of privacy. Okay, so that concludes the privacy analysis. And again, note that we've our final result is going to be oft times root p times log to the 1 over p of k. So you can see here that the root p is arising from basically the privacy analysis and the need to use the larger sigma to make up for the fact that generalized Gaussian has larger average coordinates than a Gaussian. Okay, so now let's move on to the error analysis, and the error analysis will end up being a lot simpler. So basically, we know we add noise x to d with probability proportional to exponential negative LP norm of p to the p. So again, just using change of variables, this tells us that basically LP norm of x to the p with the scaling factor sigma included, it has a gamma distribution with mean k over p. And with a little bit of work, this implies that the expectation of the LP norm of x is k to the 1 over p divided by sigma, or times sigma. Okay, so then we just show a short lemma, which says that the expectation of the L infinity norm is this ratio times the expectation of the LP norm. And then this combined with the expectation of the LP norm basically just gives us the final error bound we want. So how do we prove this lemma? So the lemma basically just follows by tail bounding each coordinate of x drawn from a generalized Gaussian and then applying a union bound. And the idea is to get the tail bound, let's assume we know what expectation of xp, or the LP norm, let's assume that the LP norm of x is fixed. So we're sampling really from the sphere, the LP sphere with a fixed radius. And we want to know what's the probability that one coordinate exceeds r. Well, we can just look at the region on this sphere where this coordinate exceeds r. And just some simple geometry tells us that in one dimension, the sphere cap is basically the region where this coordinate exceeds r is a sphere cap, which basically just looks like a hemisphere, but with the dimensions rescaled to be a length 1 over 1 minus r, and then all the other dimensions have length 1 minus r to the p, all to the 1 over p. Okay, so just basically just using some geometry, we're able to upper bound the volume of the sphere cap, which in turn gives us the desired tail bound. And then if we just take a union bound over all the coordinates, then this gives us the desired bound on the largest coordinates in expectation. Okay, so that concludes the analysis, and I'll just finish up by talking about some interesting future directions in this line of work. So one thing is that in our paper, while we do give constants in our bounds, we didn't attempt to optimize these constants, and so these constants are probably pretty far from what can actually be shown. So it would be nice to get theoretical guarantees for the generalized Gaussian mechanism that come with constants that are closer to optimal and ideally like practical. Yeah, because I guess obviously with any project like this, the goal is that eventually these mechanisms can be deployed in practice. Now, of course, in practice, one could always just use an experiment to come up with some pretty good estimate of what the appropriate choice of sigma is, for example. But from the theory perspective, it would also be nice to have strict theoretical guarantees coming with exact constants that are optimized. Okay, so another interesting direction is showing that generalized Gaussian mechanisms satisfy stronger or other notions of privacy more generally, such as Renyi differential privacy or zero concentrated differential privacy. Our analysis seems to be falling a little bit short of doing this, mostly because we are allowed to operate in the regime where delta is sufficiently large, rather than having to worry about all delta. Whereas definitions like RDP and ZCDP, in some sense, are worried about sort of tail bounds for all delta. So in particular, like our analysis shows something like that the privacy loss of the generalized Gaussian mechanism is sub-Gaussian up until a certain point where delta starts becoming small. And then once delta becomes small, we don't know if our analysis can even show a sub-exponential bound on the privacy loss, which is the type of bound you'd want for RDP or ZCDP. So it would obviously be very useful to prove the generalized Gaussian satisfies these other notions of privacy, but it would also probably require probably an improved analysis that improves our understanding of the mechanism and the distribution. Okay, and then lastly, sort of the qualitative or impact goal of this project is really that, here's a problem where the Gaussian mechanism was sort of the ubiquitous answer, but really just this very simple swap of replacing the Gaussian with a generalized Gaussian just gives immediate improvement. And it would be interesting to see if there are other applications, whether in theory or practice, where one could use a generalized Gaussian instead of a Gaussian and obtain better results. Great. Thank you so much for watching, and I'd be very happy to take questions offline or in any of the in-person parts of the conference. Thank you.